Hello, my name is Alyssa Harding, and today I'll be presenting the Blue Team's final presentation for Integrated Environmental Systems course at DU. Today we'll be talking about a system perspective on carbon capture and storage technology as a bridge to a clean energy economy. To kick things off, I'll give you a background on the issue. The system governing carbon concentration in the atmosphere is an unsustainable one. In a nonlinear world, systems like the carbon system are often structured in ways that produce problematic behavior. This creates various traps where opportunities are needed in order to balance the system. As we have discussed, when looking for new technologies and opportunities to transition to a clean economy, it's important to start with a systems level approach. Systems traps, like the tragedy of the commons, occur when the system has delays, nonlinearities, and a lack of firm boundaries that regulate natural resources. This leads to an imbalance in the flows of stocks across the system. The main issue with carbon concentration in the atmosphere is due to the imbalance of greater inflow of anthropogenic emissions compared to the outflow of natural dissipation. Additionally, the continued global reliance on fossil fuels and natural gas combustion in order to meet energy demand is adding carbon that is over 100 million years old to our present carbon system, creating additional imbalances in the stocks and flows. Today, fossil fuels and natural gas are the leading sources of energy in the United States. The driving force for the system is the continuously increasing human demand for reliable, accessible, and affordable energy. This increasing demand for energy forces pressure on the system because the majority of energy sources that are being exploited today in the United States and globally release carbon dioxide emissions and additional greenhouse gases into the atmosphere, disrupting the naturally occurring systems. Though this does sound very daunting, there are some opportunities here. There are a variety of natural and technological carbon capture and storage sequestration strategies that are available today, and technological solutions like capturing carbon dioxide emissions from industrial hotspots, which can be used as an opportunity to bridge iterative modernization of the energy infrastructure over time. Carbon capture and storage is not a new technology. In fact, companies have been extracting carbon dioxide from industrial processes since the 1930s. Carbon capture and storage can serve as an opportunity to proactively address this system imbalance. The research that we'll discuss today presents a system analysis of the concentration of carbon in the atmosphere and provides recommendations on ways to manage emissions realistically through CCS technologies. Again, our research is aligned with using a portfolio approach to meet energy consumption levels and reduce carbon dioxide emissions. Basically, carbon capture and storage is just one solution that should be leveraged as a part of a portfolio to reduce overall carbon emissions. Carbon capture and storage can help to bridge the gap in the energy portfolio approach and can be easily implemented while meeting baseload demand to help alleviate some of the pressure within the system. This research will provide recommendations on ways to manage the inflow and outflow within the system using CCS technologies, including point source capture and capture of carbon previously emitted, as well as policy recommendations to ensure that technological integration is rooted in systems thinking.
Carbon capture and storage development and utilization at fossil fuel-based energy sites would lessen the overall amount of carbon dioxide based emissions and other greenhouse gases from the atmosphere, causing positive impacts on all the interconnected spheres. The impacts carbon capture and storage can have on the spheres would overall be very beneficial. The concentration of carbon dioxide in the atmosphere in the year 2020 alone was recorded at 412.5 parts per million. This has caused a ripple effect in the spheres and has led to many issues such as ocean acidification in the hydrosphere, heat absorption and desertification in the lithosphere, and has threatened the health of every species, including humans, and giving them a higher danger and increased mortality rate in the biosphere, and has worsened land degradation. Carbon dioxide emissions are currently responsible for negatively affecting 19% of the total amount of species currently listed on the endangered species list, making their overall chance for survival worse. It is estimated that air pollution from fossil fuel-based energy plants are responsible for negatively impacting human health for more than 8 million people globally. Storing and capturing carbon emissions from the atmosphere would be to the benefit of human health and enhance the economics associated with carbon dioxide. Internationally, carbon capture and storage is being utilized to enhance residential and commercial properties. Property concerns in heat capacity issues were raised originally by residents and homeowners in Sweden and France about their home's value, the safety for them and their families being located near carbon storage facilities, and the overall community character for these neighborhoods was in question. If the correct balance and public access and education to information about carbon capture and storage technology was struck during the time of the initial development on these properties in Sweden and France, society would have had a more adaptive and accepting perspective on carbon capture and storage potential and would have helped increase the benefits. Carbon capture and storage is not without its environmental imperfections. Public opinion and misinformation often plagues the development of carbon capture and escalates concerns over natural resource depletion. Natural resource depletion from carbon capture and storage will not offset more greenhouse gases and carbon dioxide-based emissions than it is able to prevent from disrupting the atmosphere. Due to the current human application and process for carbon capture and storage, the overall mechanical process and efficiency concerns are also present. Another concern is the metal depletion and emissions caused from the metal production process for the carbon storage containers. The necessary production increase for metal containers will be required to properly and safely store the captured carbon from the carbon capture and storage process. It is estimated that for every ton of steel that is produced for metal production, that 1.85 tons of carbon dioxide is emitted, worsening the total carbon dioxide emissions significantly. Overall, the environmental concerns associated with carbon capture and storage are present, but with emerging advances in clean and renewable energies, many of these flaws have the potential to be offset, lessened, and hopefully removed. The carbon capture and storage process traps emissions from heavy industrial power generation processes in facilities, and it effectively reduces emissions and impacts on the atmosphere, hydrosphere, lithosphere, and biosphere, and can serve as a bridge during the transitional period to cleaner energy sources while continuing to help meet consumption rates and lowering our global carbon emissions.
Meeting growing energy demands while reducing carbon dioxide emissions requires a portfolio approach that includes carbon capture and storage technologies, or CCS. CCS is the process by which carbon dioxide is trapped from fossil fuel combustion and is stored so that it is not released into the atmosphere. CCS technologies are capable of reducing worldwide emissions by upwards of 10 gigatons per year and could therefore act as a bridge to cleaner energy technologies. The driving force in this system is the growing demand for dependable and affordable energy. Our world and infrastructure rely so heavily on energy that this demand must be met. However, most of the energy sources that are used today release carbon dioxide into the atmosphere, which puts pressure on the system, increasing the stock of atmospheric carbon dioxide. Unfortunately, natural sinks and the natural dissipation of carbon dioxide is outweighed by the inflow of carbon dioxide from burning fossil fuels for energy production. This image is a system diagram depicting the current system regarding energy demand and carbon dioxide emissions. As you can see, the inflow of carbon dioxide into the system from the combustion of fossil fuels alone is far greater than the outflows provided by natural dissipation and other natural sinks, such as oceans and photosynthetic plants, both of which are becoming less impactful as a result of environmental concerns. As pressure within the system grows, along with increasing energy demand, increased atmospheric carbon dioxide levels create additional climate change impacts. These require additional energy to address, further driving up energy demand and creating a destructive feedback loop within the system. This image is a system diagram depicting an alternative system that employs CCS technology. The biggest difference here being the additional sink that CCS provides in the form of direct capture, which prevents carbon dioxide from being released into the atmosphere, and as a remediation method for the existing carbon dioxide stock. Removing some carbon dioxide from the system relieves pressure on the system and should eliminate destructive feedback loops. But as you can see, CCS doesn't remove all carbon dioxide emissions from the system, still highlighting the need for a portfolio approach to the system. The carbon dioxide that is taken out by CCS can be stored and therefore removed from the system in several ways, including being injected underground, being added into industrial materials such as concrete, or as a feedstock for energy fuels.
So as we've seen, the global demand for reliable and affordable energy has led to a global energy system that generates large amounts of carbon dioxide, primarily through the combustion of fossil fuels. In 2019, human energy-related systems emitted over 33.1 billion metric tons of carbon dioxide to the atmosphere, which overwhelms the natural system balances of emissions and absorption. There are various signs that climate change is occurring due to the increased temperatures from these emissions that include things like drought and tropical storms becoming longer and more extreme, reduced snowpack and glaciers, melting permafrost that releases methane, and sea level rise and ocean acidification, just to name a few. While threshold and tipping points for each of these elements can be difficult to predict and understand, it's clear that efforts to mitigate these issues is critical to avoiding even greater impacts, and that humans are responsible for these issues. According to the Intergovernmental Panel on Climate Change, carbon capture and sequestration technology can contribute 15 to 55% of mitigation efforts worldwide by 2100. Nearly 10% by 2050, as seen in the graphic on the right, if technology is in fact implemented. Continued release of carbon dioxide is unsustainable for the global energy system, and carbon capture and sequestration can be a useful tool in minimizing impacts to the environment. Not only is carbon dioxide emissions from an energy system creating unsustainable issues for the environment, but it also creates large and unsustainable economic issues as well. The environmental issues that were shown on the last slide before create economic damages that have been increasing in recent years by billions of dollars annually. According to the National Petroleum Council, it would cost only $15 billion over the next 10 years to implement the research, development, storage, and use of CCS technologies, when compared to the hundreds of billions of dollars seen in global disasters in the U.S. alone, as the graphic on the right shows. It's a small amount when compared to the cost of those damages. They are also easily implemented while still investing in carbon-free renewables, so that small cost doesn't take away from further penetration of renewables. Many CCS projects already have lower costs per ton of carbon removed than the social cost of carbon recently set by the Biden administration. This indicates that CCS is a cost-effective method to remove carbon from the atmosphere that also helps support renewable energy development by allowing current fossil fuel infrastructure to be used to provide baseload energy needs, while renewable baseload technologies and intermittent technologies are developed and implemented further. In addition to the environmental and economic aspects, it's important to consider the social aspects of our global energy system as well. It's estimated that fossil fuel-based air pollution is responsible for nearly 8 million human deaths annually, a clearly unsustainable social issue. So in addition to climate change impacts from carbon emissions, It also creates equity, poverty, and quality of life issues as well that impact developing nations more than developed nations that profited from the externalization of the cost of carbon. Even considering these issues, though, there's been little progress made in correcting the unsustainable social issues from our global energy systems. Policies that directly restrict carbon emissions can often see policy resistance and rule-beating behavior from the fossil fuel industry and other actors like investment banks, who profit from the loans to those businesses due to the lack of alignment in goals. With fossil fuel industries and the banks that invest in them accounting for nearly $19 trillion in the global economy, policies that do not provide them flexible solutions towards the ultimate goal of carbon reduction are likely unable to pass the political process due to lobbying and corporate influences on government, in addition to the wasted effort to enforce a large resistance sector. So the social inertia present in the fossil fuel economy should not be ignored. A flexible policy, like a carbon tax, can not only be utilized to redistribute wealth to mitigate climate change efforts, it can also incentivize companies to move towards the important goal of carbon emission reductions, while enabling market efficiencies and collaboration to allow those businesses to focus on finding methods, like CCS, to decarbonize that allow them to transition without major disruptions to global and social economic systems. The global energy system is currently unsustainable in all the triple bottom line categories. However, the implementation of CCS technology can help reduce economic losses while acting as a bridge technology that allows social systems and businesses to transition to a net zero energy system by creating a new system loop that greatly reduces carbon dioxide ending up in the atmosphere as a sink.
First two systems changes, which are establishing a cost for carbon and educating the public about CCS, are aimed at the tragedy of commons trap. The recommendation to establish a cost of carbon is derived from leverage point 5, rules, incentives, punishments, and constraints. This effectively privatizes the common resource of the atmosphere, and financial consequences will be felt by all users. The recommendation to educate the public is a solution to the tragedy of the commons, as it uses leverage point 6, information flows, the structure of who does and does not have access to information, by providing users the information they need to make competent and aware decisions, which are those that avoid exploiting the commonly shared natural capital. The third systems recommendation, CCS as a bridge for clean energy, involves the policy resistance trap by facilitating the continued use of fossil fuels while the clean energy transition takes place. This is leverage point 11, buffers. This way, the energy industry is not ripped in several directions, fighting for contradictory and perversely incentivized energy policies. By emphasizing environmental value over financial benefit, the system will utilize leverage point 1, transcending paradigms, and overcoming the seeking the wrong goal trap. This would be a departure from the current paradigm, which focuses on cost as the main driver of energy-related decisions. Finally, by reinforcing feedback loops, which is leverage point 7. Based on the benefits of CCS, the drift to low performance trap is avoided by evading destructive feedback loops based on negative bases related to CCS. This is our last slide, the conclusion. There are 3 main key takeaways here. First, CCS bridges gaps in legislative partisanship by compromising short-term continuation of fossil fuel dependency or pollution reduction strategies. Second, although CCS is one of the most cost-effective technologies for climate change mitigation, it is not immune to the barriers presented by the current economic model and will require a revision of energy policies to give the service a tangible and marketable value. Third, CCS is technically sound, yet one of the greatest challenges to large-scale implementation will be educating the public and successfully executing demonstration projects to show private financiers that it is a low-risk alternative. Thank you for your attention, and we welcome any questions and comments. Have a great day.